Welcome to Data Skeptic Machine Intelligence, our podcast series exploring contemporary topics in artificial general intelligence and large language models. In today's interview, we talk about the game Hanabi. I suspect most listeners have never played it, but you might be hearing about it more and more because the AI community is getting increasingly interested in it. They keep beating all the other games. Hanabi is a cooperative game, which is sort of interesting and unique. Well, not unique, but somewhat uncommon. The players are working together. You've got common information on the board and private information in the cards in your hand. And although you're on the same team, you're not allowed to just tell the other players anything you want. There are rules governing what information you can convey, what hints you can give, and under what circumstances you can do that. During the turn, you can either give a clue to a teammate, you can play a card into the fireworks display being worked on. That's what the game's all about, fireworks, surprisingly. Or you can discard a card, which fits into a strategy all its own. And the very mechanics of the game, sort of the cooperative nature of the game, implicitly forces players to have aspects of theory of mind. If you're cooperating and sharing information through this hint system, surely you have an understanding of the agency of the other player to receive your hint. And even you must have some expectations about how they will interpret that hint and what future advantageous actions they will take as a result. This is obviously a multi-agent systems approach, and there are many models in that domain. The framework we're going to discuss in the interview is interesting in several ways. There are mechanisms in place that allow agents to change their own minds, and of course build estimates about other minds in order to play this game.
My name is Nieves Montes, and I'm a Ph.D. student at the Artificial Intelligence Research Institute in Barcelona, Spain, which is affiliated with the Spanish National Research Council.
Well, I imagine there's no shortage of interesting things for that group to be working on. Before we get into your specific work, are there any general areas you and your colleagues have a focus in?
So our department is called the Multi-Agent Systems Department. So they've been looking at things like electronic institutions, agreement technologies, coordination, distribution, things like that. In the last few years, we have taken quite a turn and started looking into values, ethical considerations of AI, because we are based in Europe, and this is quite a hot topic in Europe right now. So yeah, that is broadly our research.
Well, multi-agent systems is a area that's been around for many decades, although that means it's existed before there were large language models, before there was deep learning. There are new methods all the time. Do you have any general thoughts on the way the field has evolved?
So multi-agent systems, as you said, has been it's not one of these very very young, very new hot topics. I think it's mostly interesting because it deals with not just how programs behave in a vacuum, but how software, how different AIs are going to interact with one another. And it's a field that is malleable in the sense that it can adapt to the techniques that are currently being used. So at first it was always symbolic agents, logic-based agents. Now there's a lot of multi-agent reinforcement learning that uses neural networks and machine learning models and the such. It kind of cuts across all other subfields within our AI.
And when it comes to your own work and what you're doing for your PhD, can you talk a little bit to some of the specifics you're looking into?
I've actually been taking a look at quite a few topics and then looking to integrate them all. So I've been mostly researching value-based reasoning, so reasoning in terms of values. How is that connected to norms and regulations, and how the way we coordinate a multi-agent system can be reflective of the values that we want the system to hold on. And then coming closer to the end of my PhD, my supervisors and I realized that one aspect that is missing from all of this very, very fancy reasoning is the social aspect of values. Agents have to be able to reason not just from their own perspective, but from the perspective of others. And that's where the agent model that I developed comes in, where you just have the ability to sort of change their own minds, build an estimation of the minds of others, and work from there.
When I've been exposed to value-based reasoning, when I think of like the textbook version, it's that the vacuum gets maybe minus 100 if it bumps into the wall, or minus 10 if it cleans when it doesn't need to clean. And it's this sort of low-level values you assign to each action. But when you described it, you were saying, our values as a society. I don't know that
Mhm.
it's, -1 for crossing the street when the light is red. Can you represent it in the same way?
Yeah, so what you're referring to would be kind of the utilitarian approach, right? One dimensional, you assign some value, this is a bit of a redundant word, but anyway, to some action or some outcome. And within the agent based multi agent systems community, there's a tiny explosion of methods that look to introduce values into the reasoning of agents. So you can use values to plan beforehand, or you can reason about your actions, reason about sequences of actions, and things like that.
Well, I think people who have some background in AI will be familiar with the idea of a belief over the state space. Like if we're playing a board game, we can both see what's common on the board, and maybe I can have some estimate of what cards you have in your private information in your hand, something like this. But so I think conceptually people get that. How do we represent that mathematically?
I mean, there are different approaches. If you have a machine learning model, let's say a neural network, because that's the most usual one, the beliefs are kind of implicit. The beliefs of the relationship between input and output are kind of implicit within all the parameters of the neural network. The approach that I've been working on, it's kind of more explicit, where beliefs are stated using a logical language. Of course, beliefs may be wrong, they may be incomplete. If you foresee that any of those two things are going to happen, you have maybe to add some additional techniques for handling those. So essentially, because I'm assuming that maybe most people who listen to your podcast are very familiar with neural networks or machine learning models. But for example, in a symbolic based AI, if you want to represent a belief that it's cloudy outside, you just put the word cloudy, dot, cloudy period, and that's it. So it's kind of this very straightforward way of representing beliefs. But the drawback that it has is that compared to large neural networks and large language models, neural machine learning models, it doesn't have the ability to infer from data, to build connections on its own, to learn essentially.
Well, I definitely want to unpack the model itself and how it gets to that learning, but maybe to make sure all listeners are on the same page, we should do a few definitions. Theory of mind and abduction, I think, are two key topics we're going to get to a lot in this discussion, and maybe they're best defined as twins, kind of. Could you share a quick informal definition? What is theory of mind and what is abduction?
Yes, of course. So, theory of mind, this is a term that comes from psychology, social psychology, more precisely. It's the cognitive ability that we have to interpret others in terms of their mental states. Let me give you an example because this definition is quite abstract. So, if I see that you are moving towards the door, I might infer, oh, Kyle wants to go outside, right? So I'm inferring a desire of yours. I don't know what your desires are. I don't know what's inside your mind. At any given moment, I interpret your action in terms of your desire. You want to go for a walk, right? So that is essentially a theory of mind. This is an ability that develops during a very early childhood. And then abduction is related, but let's say kind of complementary to theory of mind. So abduction comes from the more formal field of logical reasoning and is essentially the inference of explanations for observations. So in logical inference, you have A implies B, you observe A, hence you infer B. In abduction, how it works is you know that A implies B, you observe B, and you say, okay, A is a suitable explanation for what I have just observed. So it kind of goes backward. It's also applying the example I just gave you, right? So I observed you taking an action, right? Moving towards the door. And I inferred that your motivation for that was a desire to go for a walk.
And how do you represent that in an agent? Is it sort of the first order way you've described earlier that Kyle wants a walk, or is there more structure to it?
Actually, you represent it using predicate logic. It's called first order logic, but it reads relatively similar to English. So it would be desire, open bracket, Kyle, go outside, close bracket. It is really quite readable, quite explainable, and I don't know if we're going to get into the explainability or not, but this is one of the advantages that symbolic methods have over machine learning slash statistical methods. It's their explainability because you really write and read them as English.
Well, it seems as though you need some sort of software engine or an algorithm here that can take all of these inputs and do some inferencing and produce new knowledge or something like this. I guess, what's at the core here?
Right, so that's the interpreter. Of course, a fundamental component of any symbolic based agent. In our work, what we did is we developed a model, an agent based model that could do the inference analogous to the example I just gave you. Cow is moving towards the door. As input, you have the observation of an action, and you have in your knowledge the set of rules that could lead to the desire of going outside, right? And you go through these rules and you see what is the motivation. So, what is the precondition for those rules? From those preconditions, you build an explanation. So, for example, maybe you're a very outgoing person. When I see you going towards the door, I assume you want to go for a hike. But maybe Bob is not so outgoing and he only wants to go out because he needs to get groceries. So, if I know that Bob is not very outgoing, the explanation, the motivation that I'm going to assign to Bob is going to be different. Bob wants to go to get groceries, Cal wants to go for a hike. It's a very dumb example, but it sort of captures the mechanics of the modeling.
Well, I'd like to zoom in on the particular use case you explored most in the paper, the game of, I believe it's called Hanabi. I have a vague familiarity with it. Could you share just some details on the game and then maybe discuss why it's an interesting problem for your framework?
Yeah, it is definitely a very interesting problem, not just for my framework, but for AI in general. There have been good results for Hanabi just by using huge learning models. What we wanted or machine learning models, let's say traditional machine learning models, what we wanted to capture was more of the psychological processes that go in when you play Hanabi. So to set the stage, Hanabi is a game that is played in a group, but it's cooperative, right? You're not competing against each other, you are all part of one team, and you get a set of cards. Each player gets a set of cards, and the cards are placed in a way such that you don't see your own hand, but you do see the cards of others. Every card has a color and a rank, so you have red from 1, 2, 3, 4, 5, white 1, 2, 3, 4, 5, and you have 5 different colors, if I remember correctly. The idea is that you have to play your cards to build stacks. So you have to build the red stack. So red 1, red 2, up to red 5. You have to build the white stack, white 1, white 2, up to white 5. So you have to play your own cards, but you don't see your own cards, nor does everybody else see their own cards. So you have to exchange information, and the game allows to give you hints to one another about either the color or the rank of their cards. So this is, let's say, the basics of the rules. By the way, I recommend that if any of you gets the opportunity to play it, you should try it because it can get very fun. Because there are people who, let's say, flow very easily, and then there are people who don't understand anything. So it's a fun game to play. So this game is very well suited to our model and partially inspired our model because it's a game that necessarily needs a theory of mind. You need theory of mind to work well. So you need to reason about what does another player know, what do they need to know in order to play a card that is going to increase our score. How can I give them that information? And the same works in the other direction, right? So when I get a hint or someone does, let's say, some general action, what were they meaning by that? Do they want me to play this card? Do they want me to save it for later? Do they want me to discard? So that is where the abduction comes in. And of course, this abduction has to be performed from the perspective of the person who is quote unquote communicating with you through their moves in the game. As usual in AI, we like these pretty benchmarks, right? So this is not an open world problem. So this is very defined and it's very suitable to test these new techniques and these new models.
Yet still a pretty challenging game, I think.
Yes, it is. It's challenging, and it also has quite an active community of online players. And these folks have developed a whole set of, they call them conventions. So these are essentially guidelines for how to play the game or what strategies to follow. And these are itemized by the level of the players, so whether they're newcomers or whether they're experts and so on. So I think there's quite a lot of work to be done in digging up through those conventions and seeing how they can be then input to the model, see how the model works, see how the model also interacts with humans. That would be something very interesting to see. Yeah.
So you'd mentioned that the agents in your framework can change their own minds. Is that through the abduction process that's sort of like learning new facts, or is there anything probabilistic about it?
Okay, first of all, to clarify, the changing mind part, that is purely a theory of mind process, or let's say our modelization of how theory of mind works. It's a particular branch of theory of mind, which is simulation theory of mind, which is opposed to theory of mind. But okay, this is a side note. So, not yet. We haven't considered probabilities yet, in part because we were quite oriented to the use case. And when you start computing probabilities in Hanabi, if you want to compute them, let's say exactly given the information that you have, it gets very large very fast. You have to consider temporal considerations. When did you learn about what? How does that change the probabilities that you have? We didn't look into that. However, I believe that our framework is broad enough that it could be, so that there are a few functions in there that could be used to incorporate probabilistic considerations. But the short answer is that at the moment we have not.
Yet, despite that, we see some good performance in the game, which we'll get to as think we get into the conclusions. But before that, maybe we can zoom in on and you'll have to tell me how to say it. Is it Tom ABD or Tom Abd?
However you want to
Yeah.
to
What is the
pronounce
Tom
it.
Abd agent model?
Tom ABD. I would
Tom
say Tom
ABD.
ABD, but it's not the prettiest name, but it was kind of the logical. So theory of mind abduction.
Well, multi-agent systems has never been famous for clever names, so I like it.
That is true.
But could you describe the tuple and what each of the pieces do?
Okay, this is a general abductive logic programming definition. This is not particular to our model, so we sort of take it and adapt it. I mean, so essentially, to perform abduction, you need to have some theory of how the world works or how the game in our particular use case works. You need to some extent to know what can be missing from that theory, and then you may have a set of constraints. And what abduction does is that it takes this theory plus an observation and it does some logical inference to arrive to an explanation for the observation. So that's essentially it. This is like purely background. This is not specific to our model.
And then how do you go from that update process to choosing an optimal action?
Actually, choosing an optimal action is not something we have focused so much. So we have focused in an agent, you have, let's say, three basic steps. So the first is perception. So you observe the environment and or you get information or you observe others. Okay, maybe you want to assume that others are part of the environment or not. Anyway, the second is deliberation. So essentially, what do you do with that information? Do you update your beliefs? Do you choose your next action or not? And whatnot. And then the final step is acting. That is when you have decided on an action and you execute it on your environment. This model, the weight of the model is put on the perception and deliberation aspect. So, how is the perception of another agent's action affecting your beliefs about the world? We haven't focused so much on the deliberation towards execution part, so the looking for optimal actions, because that also was, let's say, interfering with deliberation in the first place, right? So if the others already know how to reason, is it worth it for me to go and reason somehow differently, or is that going to throw them off? So that was a bit the thinking. However, that is one of the points that we do leave open for further exploration, and that is actually, I think that would be quite an exciting thing to look at. So how do you use a theory of mind during the look ahead process for deciding on the optimal action?
So you have to have some constraints that you give the player or the agent in order to understand the game world. Do you have to encode that logic, or how do you kind of give it the information it needs to stay in bounds?
Yeah, it's encoded. So I mean, the case of Hanabi, the constraints are, pretty straightforward. So just related to the physical world, right? So you cannot have two cards simultaneously in the same slot in your hand. Also about the number of cards of each color and rank that there are. For example, for every one, there are three copies of that one, but for every five, there is only one copy. So things like that. Yeah, you do have to encode them. Yeah, absolutely. You need to take those into account when you do the reasoning. You have to come up with explanations that are feasible, right? That are not impossible, because otherwise you're just reasoning with fantasy, and that isn't really adding any value to what you already know. So yeah, for sure, they are used to kind of purge out impossible explanations. Yeah.
Well, I think it's clear in Hanabi I need to reason about the beliefs of other people to learn something and advance in the game. Is it useful to reason about their beliefs about my beliefs and maybe even deeper nesting?
That that's a very good point and a very interesting question. The answer is that we're not sure, because Hanabi, for all of its interest and for all what it offers to the AI community as a benchmark, is a very symmetrical game, right? So every player has the same role. Every player is sort of in the same position with respect to others. I am not sure that going deeper in the theory of minds necessarily helps in such a symmetrical domain. There could be other domains where it would be maybe more beneficial to do that, maybe in not cooperative domains like Hanabi, but competitive domains. Yeah. And what has been found in other research on, let's say, computational approaches to theory of mind, particularly in competitive domain, and taking a whole other modeling theory of mind in a whole different way, is that the benefits kind of plateau with the deeper nesting level that you go to. So, I mean, I may be reasoning about what Kyle thinks that Bob wants, and that may bring some benefit. But if I start reasoning about what Kyle thinks that Bob wants Alice to think, there's a point where we humans get lost.
Yeah.
Computers don't get lost because they're computers, but it's not so clear that there's any benefit in that. It would be like an absolutely extraordinary finding if people found that for a broad range of computational domains, so let's say Hanabi and maybe some competitive domains where theory of mind is kind of a factor, it would be an extraordinary finding if people found that the performance plateaus right at the levels where we humans are not able to go any deeper. That would be like the finding of a lifetime, I think.
Well, when it comes to then the performance of these agents, how can you analyze their play and say the quality to which they're getting following the abduction process?
So this is something that is not, let's say, the performance in terms of, say, not in terms of low-level computational performance like execution time, memory, things like that, but in terms of, let's say, score, is something that you have to define for every domain in particular. So, for example, in Hanabi, there's a very straightforward metric, which is the score at the end of the game, right? So you have to build these stacks with your peers, and at the end of the game, you count the height of each stack, you add it up, and that's your score, right? And it may be the case that you lose your lives before that happens, and then you get a zero. So that is very straightforward. We got decent performance along that metric, but actually the metric that I think is even more interesting than just the raw performance, and that I haven't seen any other researchers use, is what we called it communication efficiency. So the communication efficiency is defined as the ratio between the final score and the number of hints that have been provided. And we think that is a very interesting metric because with that you quantify how efficient your players are at turning communication, so information exchange, into utility. And that kind of breaches two, let's say, research lines within AI or within agent-based models, more specifically, which is communication and utility-based approaches.
Well, when I think of like a machine learning approach in which we gather a lot of features and ask machine learning to figure out which features to use in making some prediction or inference, you can add new features. Maybe they'll be good ones, maybe they won't. Like, I think of like a weather feature. If you're trying to predict car accidents, weather's probably helpful. If you're trying to predict whether or not a document is a positive or negative sentiment, the weather doesn't matter at all to this document. When you give agents the facilities to use theory of mind, do they take advantage of them?
Well, they take advantage of them if their interpreter, what is called the interpreter, which does this cycle of perceive, deliberate, act, if they are, let's say, quote unquote, told to use theory of mind in that process. In our approach, what we did is we are going to keep all the theory of mind capabilities to be triggered, let's say, at the agent designer wish. So it's agents so far do not, let's say, autonomously learn to trigger their theory of mind, although that could be a very cool thing to look into, because we were not interested in that particular phenomenon. We were more interested in what are the benefits of theory of mind and so on. So we kept it, let's say, as a button that you can push.
Sure. Well, then, when comparing the button being on or off, do you see noticeable behavioral changes in agents that are using theory of mind?
Yes, we do see more, certainly for the Hanabi domain, we see more beneficial perform, let's say more beneficial behavior, which ultimately leads to better performance. So we see gains, and this has been statistically tested and so on. We see gains for score, we see gains for communication efficiency. So yeah, we do definitely see gains. However, since this is a domain dependent, let's say, so that the evaluation of the model performance is a domain dependent thing, And for each domain that you would want to apply, you would have to define, okay, how do I define performance in this domain? So if you have board games, it's usually quite easy. And then see from that what is the gain in performance when you have theory of mind on versus when you have it off. And then if you want to go deeper, you can see what is the performance with respect to the nesting level that I have reasoned at. Okay, I may only be reasoning about Kyle, or I may be reasoning about how Kyle thinks about Bob, and then check that. Yeah.
So you know that the score and communication efficiency improve when I can apply theory of mind as an agent. Do I have to pay a computational cost for that?
Why? Yeah, definitely, because nothing, nothing is free in life.
Yep.
So the observation of other players' actions and the processing of those observations into your belief base, that is a computational burden that you have to take. Yes, of course. There's also the burden of, as I observe changes in the environment, in my environment, how do I update the explanations that I inferred previously? This is something that we also took into consideration. This factor of the computational price that you have to pay is also something that you would have to, let's say, plot with respect to the nesting level that you go. Assuming that in your domain deeper theory of mind is going to give you a performance gain, you have to weigh that against the computational price that you have to pay.
Well, if I have a choice, let's say I'm going to assemble a team of automated Hanabi players, there are lots of methods I could choose. Deep learning is something I'd probably want to consider, but I also want to consider your framework. What are some of the advantages where I would want to take your approach over something like a deep neural network?
Well, a deep neural network, there's a computational cost in developing a good neural network, a good predictor. That's one. We also have our computational cost, of course. One aspect that does let's say set our model apart is the ease of interpretability, right? So you can read, quote unquote, read what observations the player is making, how is it deriving explanations from those, and that is pretty transparent, right? Because the information is encoded using this first order logic, which is mostly like almost like English. In a deep neural network, you don't have that. I haven't seen anything specifically Hanabi learning agents and explainability. Granted, this is something that we haven't looked into detail to, but it's definitely much easier, right? So you don't really need many additional techniques to be able to interpret your agent. And also, this is, let's say, maybe not so relevant from the academic point of view, but when you are playing with a human, let's say you have a team of mixed human software players, going back to the conventions for playing Hanabi that this community has developed, if the humans agree, okay, we're going to play up to this to intermediate level because we are all in, because let's say that is the minimum level of our players. There may be some expert players, but they don't want to use all of their fancy tricks just now because other people are not so experienced, right? So maybe in that case, you want to, let's say, tone down your own agent. Don't make it play super fancy, but be better in tune to what the others are doing. And that is something that I'm not an expert in machine learning, but I'm not really sure whether you can control that kind of thing in machine learning, right? So machine learning is kind of all in. Let's get the best that we possibly can. And that is definitely great for some aspects, but maybe not so good with others, right? So maybe you don't want to teach, let's say, quantum physics to first graders. That would be the analogy.
Oh, but you want to start them somewhere, so turning the knobs like your approach allows might get them the introductory material.
Exactly. That's the idea. That you don't need to go all fancy, doing super complicated tricks if everyone else doesn't know how to do them, right? I mean, if everyone else does, then sure, go ahead. But maybe it's counterproductive.
Well, it seems like you've got a good success applying this in Hanabi. Do you have any thoughts on other domains you might want to take the approach to?
Not yet. This is, let's say, in my to do list of literature review to do. I would definitely like to go over other board games, so cooperative slash competitive cooperative board games, because those, as I said before, board games are kind of very pretty in the sense that the state is very defined, is not a real world problem. So that would kind of be the first step, and then see how it does in those situations. Yeah.
And when you look to maybe the far future, let's say there was another good paper and then some funding came along and we wanted to push this to the limits, are there any scalability challenges you will hit as you want to push this to bigger problems?
Yeah, good question. Possibly, yeah, because at the end of the day, you have to encode. For example, you have to encode constraints. You have to encode the strategy level or the strategy that the agent is going to reason upon. So yeah, I mean, if possibly this model as it is now is going to hit scalability issues. Anyway, this could probably be to some extent partly solved by, at the end of the day, integrating some learning approach, right? That is less interpretable, but that is very, very efficient at encoding information.
Yeah. It seems like this is a sort of explicit approach that wouldn't miss anything. Maybe something that's epsilon close could be just as good.
Yeah, exactly.
What's next for you?
What's next for me? Graduating.
Uh huh.
So definitely graduating. I would like to spend some time in industry just to get the experience, see what that is like, and then we'll go from there. But I'm not going to make any long term plans because at the end they never happen. So yeah, graduating, definitely.
Well, I hope you're on a good path to having that close in hand. The paper certainly speaks volumes in that direction.
Thank you very much.
Yeah, and is there anywhere listeners can follow you and your work online?
So I'm not a big social media person, but you can go to the institute's website. So that is triple IA, so three I's follows by one A, dot CSIC dot ES, and then you go straight to the English version, and then you can see my work. You can also see the work of the people of my colleagues who work there. We have, let's say, a wide range of topics covered. And then if you're more interested in the academic stuff, I would suggest you look me up on Google Scholar.
Yeah, good advice. We'll have links to both in the show notes for listeners to follow up. Nieves, thank you so much for taking the time to come on and share your work.
Thank you very much. I enjoyed this interview very much.